Hello everyone. Let me ask you something. Have you ever noticed that when lightning strikes, you see the flash first and hear the thunder later? That's because light travels much faster than sound. And that little delay is all about wave speed. So, what exactly controls how fast a wave moves through a medium? Well, the speed of a wave isn't about how loud or big it is, it's all about how the medium behaves. Imagine plucking a guitar string. The vibration rushes through the string, not because of magic, but because of tension and mass density. In short, wave speed depends on two key traits: the elasticity, how easily the medium bounces back, and the inertia, how much the medium resists motion. A tighter or more elastic medium means faster waves. A heavier or denser one means slower waves. Let's zoom in on one of the most important cases, a wave on a stretched string. Picture a small bit of the string, a tiny section with length delta x and mass nu times delta x. When you pluck the string, that little piece moves up and down, and tension in the string acts as the restoring force. Now, applying Newton's second law to that element, force equals mass times acceleration. For small angels, the restoring force is approximately equal to t multiplied by partial squared y by partial x squared times delta x, equating both sides. So what really affects the speed of a wave in different media? Let's decode it. The elastic property, like tension in a string or bulk modulus in a fluid, speeds things up. The inertial property, like density or mass per unit length, slows things down. For solids and liquids, we use V equals square root of B divided by rho, where B is bulk modulus and rho is density. For gases, thanks to Newton and Laplace, we modify it to V equals square root of gamma times P divided by rho. Here gamma is the ratio of specific heats, P is pressure, and rho again is density. Change the medium and you change the speed. That's why sound travels faster in water than in air, and even faster in steel. Now let's focus on a very familiar wave, sound in air. You might expect sound to depend on pressure, but surprise, it mostly depends on temperature. Using the relation V equals square root of gamma RT divided by m, gamma is the specific heat ratio, R is the gas constant, T is absolute temperature, and m is molar mass. As the air warms up, molecules move faster, colliding more often, passing the sound energy more quickly. That's why sound travels faster on a hot afternoon than on a chilly morning. In fact, for air, the approximate rule is V sub T equals V naught multiplied by square root of T divided by 273. Let's play a quick guessing game. Where do you think sound travels faster? In air, water, or steel? Here's the data. Air, about 343 meters per second. Water, around 1490 meters per second. Steel, roughly 5100 meters per second. That's why if you press your ear to a railway track, you'll hear an approaching train much earlier through the metal than through the air. Solids are both denser and more elastic. Elasticity wins the race. Alright, let's roll up our sleeves for a quick but beautiful derivation. We start from the wave equation on a string, y equals a sin kx minus omega t. For a fixed point on the wavefront, the phase term kx minus omega t stays constant. Differentiating with respect to time gives k times dx by dt equals omega. Rearranging, we get dx by dt equals omega divided by k, that's the wave velocity. V equals omega divided by k. Now, from the earlier derivation for a string, V equals square root of t divided by mu. Both forms tell us the same thing. Wave speed depends on the medium's properties, tension and density, not on amplitude or phase. Let's tie everything together before we wrap up. The speed of a traveling wave is simply how fast the disturbance moves through a medium, the messenger's speed of energy. For a string, V equals square root of T divided by nu. For a fluid, V equals square root of B divided by rho. For a gas, V equals square root of gamma P divided by rho, or equivalently, V equals square root of gamma RT divided by m. It increases with elasticity and temperature and decreases with density. It's not affected by how loud or how big the wave is, just by the nature of the medium itself. From the twang of a guitar string to the echo of thunder or the hum of machinery, wave speed governs how quickly the story of energy travels through matter. And that's how physicists measure the heartbeat of a medium, its wave speed. I hope this session helped you see waves not just as motion, but as messages carried through nature.